Thanks for the introduction, and really happy to be here. Like I said, it's really an adventure. And I hope to bring you more adventure in my upcoming talk. So today I'm going to talk about the Institute investigation of hydrogen-assisted crack initiation in nickel-based alloy 725. So first thing first, why do we really care about that? You might think about hydrogen as something really far from you. But thinking about the future, in the future, we're going to have like more hydrogen used as clean energy. For using that, you need somewhere to storage it and to transport it. So in that case, the material is going to be exposed in the hydrogen environment. Well, maybe you think, okay, hydrogen transportation and storage is a little bit far from us. It's still a couple years ahead. What about daily life? So the first one is actually showing a pipeline. You know, when you have a pipeline under the sea, it might undergo corrosion. And how do people usually protect it from getting corroded? They put it on the cathode side. For the metals, it generates the electrons. So it won't lose electrons to protect the metal. But on the other hand, you're just basically charging water, and then you got the hydrogen bubble on top of it. The byproduct of cathodic protection is actually hydrogen embrittlement. In the second case, you can see here we are using the electroplating. It's a similar idea. You got this material with a shiny finishing, but you also introduce it into a hydrogen environment. And third one, as we said, hydrogen transportation and storage. And because these materials can be exposed into hydrogen, we definitely don't want this to happen. And this is hydrogen embrittlement. When a metallic material exposed into the hydrogen environment, it loses its ductility and it becomes brittle failure. Without hydrogen, you can see this is a ductile sort of failure, and with hydrogen, now we see this brittle failure. So we want to understand why this happens and how can we improve that. We think about, okay, first, what is the mechanism of that? People have done research, intensive research on that, and there are many, many mechanisms. So today I'm going to introduce you two of them. One is called HEAT, which is hydrogen-enhanced decohesion, which means when hydrogen decorates a surface, the decohesive energy is reduced. And because it's reduced the bonding energy, and hydrogen embrittlement happens. The issue with this is thinking about how much energy we need. To reduce this amount of decohesion, we need a lot of hydrogen from the calculation. So then the second one is called HELP, which is hydrogen-enhanced localized plasticity. The HELP hypothesis proposed that hydrogen would enhance the localized plasticity, and the localized plasticity promotes the fracture. So there are evidence that hydrogen enhances the intrinsic mobility of individual dislocations.
While localized plasticity does promote fracture in some materials, evidence for its role in hydrogen embrittlement usually take the form of slip lines or enhanced dislocation densities observed at the fracture surface or cracks observed along the slip bands. The thing is, are those observed features the cause of the fracture or one of its effect? Regarding the material of our interest, alloy 725, this is a nickel-based alloy with good corrosion resistance and high strength. And in the industry, people use it as a structural material.
So you definitely don't want this like a sudden failure in the picture we showed before happen to this material. In the prior research, people charged it with hydrogen and then did a tensile test, saw copious secondary cracks on the surface with a primary crack in the middle. And they did some post-tensile test analysis and found preferential cracks along the coherent twin boundaries, which we call it CTB.
CTBs are the ones with the lowest energy, which means they should be more resistant to hydrogen embrittlement. But
this is a post-tensile analysis, which means we see everything after it happens. The crack is already there, crack already initiate and propagate. We don't know exactly how it happens, And if you remember the question we had before, is the slip traces the cause or is it its effect, right? We still don't know what is the role of the slip. How can we observe the crack initiation? And by the way, all of these experiments have done with only one hydrogen content. It's just change single charging, you go there. But what if we change the hydrogen content from low to high and see if there's any correlation?
To achieve these goals, we need to conduct experiment in situ inside of the SEM and observe the changes while they are happening.
So today I'm going to talk about three things. The first is, how does the slip change with hydrogen content? The second thing is the localized plasticity really necessary for our crack initiation? The third thing is, remember we talked about hydrogen could come from different ways, right? It could be from the cathodic side, or it could be from the environment, gaseous environment. Would the behavior change as we change the mean of hydrogen ingress? So let's take a look at how we prepare our sample. So I got a specimen look like this. You see, this is a standard dog bone. And in the middle, we make it extra thin. So when we observe it under the SEM, we only observe very small area. So now we can make sure the area we observe would have crack. So we don't have to search it everywhere. And because we want to track how the slip is forming, right? Then we want to have something to be able to use it to track. So we introduce some pattern by doing some PVD thin film, and we reformat it into small nanoparticles. So we use those silver nanoparticles on the surface of our sample to track slips. After that, we introduce the hydrogen into the material with two ways. The first one is just like the cathodic protection. We put our sample at the cathodic side of this electrochemical cell and charge it at three different conditions. We alter the current density, but we keep the time to be the same. So with different current density, now we can introduce different amount of hydrogen. We burn the sample. So when you burn the sample, the hydrogen inside will turn into water. We measure the water, and then we got the hydrogen content of each sample. So if we compare that, it goes from the hydrogen-free to low, medium, and high.
As the sample we use is very thin, we can use a 1D diffusion model for this hydrogen ingress process. And we can, based on the Fick's law, to calculate the hydrogen distribution and hydrogen profile like this.
On the surface, we have good amount of hydrogen, and in the middle, we have almost no hydrogen. Well, you might wonder, why don't you charge through? Remember, what is our purpose? We want to see crack initiation. If we charge it through, the sample is going to be fully embrittled, and once we do the tensile test, what's going to happen? It's going to break. Nothing will be captured. Right?
So with the surface embrittlement, we can capture many crack initiation events. It takes 4 hours from the moment we take the sample out of this electrochemical cell to the end of tensile test. So then we also calculate the hydrogen outgassing after 4 hours, and we lose about 44% of hydrogen.
For comparison, we also did a thermal charging, which we put a sample inside of a furnace. We have this furnace full of the hydrogen environment with a particular pressure and at 300 degrees C. So theoretically, we are going to get this amount of hydrogen. But we don't have this facility. Think about what happened today, right?
So we sent the sample to Sandia National Lab, and they did the thermal hydrogen charging experiment.
And they charge the sample, they put it in the dry ice. They have all of the protocols, make it extra safe, ship it to us. So we also measured it after receiving it. And this is actually what we got. So if we compare this with our electrochemical charged one, we got slightly more hydrogen into our thermal charge sample.
Now we have different hydrogen charged samples. So we take this into SEM and did in situ tensile test.
We stop and take images at every 1 3 strain increment. and our average strain rate is 4 times the power of -5. For your information, when doing hydrogen embrittlement testing, hydrogen embrittlement happens at lower strain rate. The reason why we stop and take an image is if you have experience with SEM. If your sample is shaking, then you won't be able to get a high resolution image. So we particularly stop there. We took a couple of the image with high resolution and we stitched them together to get a bigger field. This is what we got after the tensor test. We don't have a accelerometer on that. So x-axis is elongation to the gauge length, and on y-axis is our engineering stress.
Consistent with hydrogen embrittlement, we see the elongation to failure decreases with increasing hydrogen content. And these small intermittent stress drops in the figure are corresponding to the periodic pauses for the acquisition of the SEM images. You see the electrochemical ones are all grouped here, but the thermal one has more reductions. In the meantime,
we compared the surface of the electrochemical charged one with the thermal charged one, and you actually can see it is quite different. If you look at our electrochemical charge sample, this is our primary crack, and all of these are secondary crack. But in our thermal charged ones, we only have one primary crack, and we don't have many of the secondary cracks. If we look at the fracture surface, then we find that electrochemical charged one, we have the dimples in the middle and this cleavage at the surface. This is also proving that the surface part is hydrogen embrittled, just as the hydrogen distribution we saw. And as for the thermal charged one, we have this combined cleavage and dimple sort of structure. So this makes us wondering, okay, there might be some difference between the crack initiation process in the electrochemical charge sample and the thermal charge sample. Going back to our Amos goals, we want to know how does the slip change with hydrogen content.
We know we can see surface slip under SEM, and we see more surface crack in the electrochemical charge sample.
So to better understand this question, maybe we should focus on the electrochemical charged sample
and look how the slip change with hydrogen content. Observe the surface of electrochemical charge sample in situ in the SEM while doing the tensor straining.
We'll be able to see the crack initiation, and when you see a white arrow that is pointing at the initiation site. This is a sample with the medium hydrogen content, and you see nice surface crack initiation in this case. All right, so I see the cracks, but we are talking about slips. Where are the slips? So if you take a look at this, yeah, there are some slip traces over there, but how can we quantify it? We use digital image correlation. Remember those different particles, right? If you have a particle A before the deformation, and if you track where the particle A after the deformation, now you know the displacement of A to A. Similarly, you have B to B, C to C, D to D. So we track the image before and after, we get the displacement. And with this displacement, now we can calculate strain, right? So now let's take a look at what we got in the strain map. This is a 2D deviatoric map of the sample we tested. Same location as you see where you have the crack initiation. And now on this map, blue represents where you have low strain, and the yellow is where you have high localized strain. So as we do the testing, you see those areas without any color. Those are the places where we have our crack initiated. All right, let's replay this again. First, there are some lines that is parallel together. Second, you have some lines with very bright colors localized in some region. Where are they? Is this inside of green, or is this like at green boundary? So microstructure-wise, where are they? So we correlate this one with our EBSD. And we found that the slips occurs both in the green boundaries and in the green interior, with the green boundary have the greatest slip values. And this is true regardless of the hydrogen content. Let me just show you the hydrogen-free, low hydrogen, medium hydrogen, and high hydrogen, all of these maps.
All of these three maps are taken at elongation to gauge length of 0.11. In all cases, we observe qualitatively similar strain distribution trend. The majority of the surface strain are near or above the average deviatoric strain, while there are some isolated bands that have strains well above the average deviatoric strain. And these long linear bands are corresponding to the trace of slip bands intersecting the surface.
So if we take all of this deviatoric strain data, and if we plot
the distribution of deviatoric strain over the average deviatoric strain for all four samples, then uniform plasticity would expect to yield sharply peaked distribution like this, and the border ones, especially with long tails at higher values, would indicate greater localized flow.
So how would our field look like? Ours looks like this. You find distribution for all four samples are relatively broad.
This is consistent with our qualitative observation that flow is localized into discrete slip bands. Also, there are no monotonic trends in the shapes of these distribution as a function of hydrogen content. So the degree of localized plasticity in hydrogen charged samples is comparable.
So we can conclude that in this case, hydrogen has no effect on the strain localization. Do you see any trend? Okay, let's move on to the second part, which is localized plasticity really necessary for crack initiation? We take a closer look into our material, and we see there are two types of crack initiation event.
One with nearby slip, the other without. In this figure, red lines represent twin boundaries and black lines are the non-twin green boundaries. The first stream map is right before the crack initiation. The second stream map is at initiation. In the first case, crack initiate with localized slip, as you see the yellow here, and this slip is actually along CTB.
This is the first time that cracks initiate with a adjacent slipping boundary.
In the second case, you can see the crack initiate actually inside of green interior, and there is no nearby slip. The last strain image, which we know crack already initiated, we see this high deviatoric strain region, but this is actually due to the crack opening displacement, not a slip. This is the second type, crack initiate without nearby slip, and usually this sort of event occurs at locations where we see a surface flaw or impurity, and you see here we have a fib mark nearby. So we count the type and number of these crack initiation events in each of the sample, and we plot this as a function of hydrogen content, as you see here. When there is no hydrogen, we didn't observe any crack, and as the hydrogen content increase, so does the number of initiated surface cracks. As for the crack initiation type, at low hydrogen content, all cracks initiate with the high slip region, and at the highest hydrogen content, most initiation events are not preceded by the nearby slip.
So that means with more hydrogen, the more crack would initiate without slip. So what is the role of slip in this case? And can we even further quantify this? Let's take a look at one of the cases. I'm going to explain how we did this slip analysis. So this is our slipping boundary, this yellow one, slipping boundary. The crack initiates at this point where we have this black one. And this red color marked where we have the thin twin, it is also a CTB. Because we did this digital image correlation, we compared how it shifted from image 1 to image 2, we got displacement. Originally, the displacement is along U direction. Now, if we take the slipping boundary, and if we transfer this V and U into this T and N direction, T means it's tangential and N means it's normal, just along the direction of the slipping boundary. Then, if we plot this T value displacement, tangential displacement, across the slipping boundary along the direction of this white dash arrow, now what we get is, okay, here we have value, here we have a T value, and here we have a discontinuity. We take this discontinuity as our slip value. And then we took all of these numbers across this boundary. If we take this particular boundary, this is where the crack initiates. And if we plot the slip value along this slipping boundary
with different tensile elongation, and we found that first, as the elongation increases, slip value increases. Second, we can see
here we have the highest slipping value. Here is where our crack initiates. Our crack does not initiate as a location with the highest slip.
So we performed this analysis at multiple locations along all of slipping boundaries for different tensile elongation for all of the samples. And for each sample, at least we have 600 points of interest for analysis, and we found the trend to be consistent.
So where does it initiate? We took two cases. In the first cases, we have this crack initiated in this area where we have this slipping boundary, and the slipping boundary is facing a very thin twin. The slip stopped here. In the second cases, we do not observe any cracks in this case. Here we have a triple junction, and this concentrated strain going through this triple junction. What we see here is the main role of the slip in crack initiation is to generate local stress concentration. So we answered the second question. Is localized plasticity necessary for crack initiation? So we observed many cracks initiate in the area with no apparent localized slip. As the hydrogen constant increase, we see more and more initiate without any nearby slip. Let's move on to the third question. Would the behavior change as we change the mean of hydrogen ingress? As we keep on loading, we see some slip traces, and then we just see one of this crack. This cracks later on becomes our primary crack. I don't have another image because the next frame, this is just completely broke. So I can no longer track it. We also did a surface strain distribution analysis of this part. And as you can see here, we did not get as many slip bands compared to what we had in our electrochemical charge sample. We're wondering, okay, so what makes it so different? Why in one case we have a lot of surface cracks, and in another case we just have one crack
and fewer slips?
So maybe there's something inside. So we took both of the sample and did a CT scan to see if there's any difference in terms of the internal crack. So this is just one slice we took from the cross-section of the material. To give a better illustration, we actually extract out the cracks and the pores inside of the material by taking the grayscale value of each of the voxels. And as you see here, the yellow and green one, they marked with different color because of the size. The yellow one and the green ones are the cracks and the pores. This is in the electrochemical charge one, and this is in the thermal charge one. So you see, in this electrochemical charge one, we got a giant crack, and there are many cracks on the surface Well, for the thermal charged one, we see cracks mostly in the middle. This is just a qualitative analysis. So how exactly does the trend differs from the electrochemical charged one to the thermal charged one? So we did this plot. We see the distribution of the quantity of the cracks to the distance to the nearest surface. We didn't use the absolute value because when the sample break, it has some slight shift. And because of the change of the sample, we cannot use the absolute value. So we measure the distance to the nearest surface. So as you can see in the electrochemical charged one, we have the majority of those distribute along 20 to 40 microns from the nearest surface. But in the thermal charged one, this shift towards 40 to 50 microns from the surface. You can also see
there's good amount of surface cracks.
But compared to the thermal ones, most of those will distribute inside and even deeper inside. So what could be the reason? This is actually still a work in progress. We got this result like 2 weeks ago. So we think maybe this has something to do with our hydrogen distribution. If we take a look at the hydrogen distribution in the electrochemical charged one, you see after the 4-hour degassing, majority of those was sitting here. So kind of matching between here and here. We still don't have the profile of the thermal charged one, but we are hoping to see how these two correlate with each other. So here are the takeaways. First, hydrogen has no effect on the strain localization. Second, as our hydrogen content increase, the more cracks initiate without nearby local slip, and the localized plasticity is not necessary for crack initiation. Third, we see more deeper internal cracks in the thermal gas charged sample, and we see most surface cracks in the electrochemical charged sample. What is this telling us? This is telling us in the future, in the application, we have to think about different hydrogen source. If you have different hydrogen source, then we need to think about how would the material behave. Also, we want to consider the hydrogen content.
All of this can help with the lifetime prediction of components operating in hydrogen environment and for the development of novel hydrogen embrittlement resistant alloys.
So I would like to thank all of those people who helped me. I did this work mostly when I was at Texas A&M with Michael Demkowicz. Lai is the person who charged the sample through the electrochemical charging. Currently, I'm at Washington Lee. Patrick and Jacob, who are both my undergraduate student, wrote those code for doing those to do those CT analysis. And we also want to thank the Sandia National Lab doing the gas charging for us. And with that, I'm happy to take any questions you may have.